Hello students. In the previous class we have learnt acidity of aliphatic carboxylic acids, and in today's class, in this video, we are going to learn acidity of aromatic carboxylic acids, right? Here the parent member of aromatic carboxylic acid is benzoic acid. Benzoic acid is having the formula, that is structural formula, C6H5, then followed by C double bond O, then followed by H. This is benzoic acid, which is a weaker acid, and it is weaker since the dissociation constant, that is acidity constant Ka, is 6.3 into 10 to the power of minus 5. Which is very less when compared with that of formic acid, because formic acid is having the acidity constant of 17.7 into 10 to the power of minus 5. Now let us have the explanation why benzoic acid is a weaker acid when compared with that of formic acid. In benzoic acid, the phenyl group that is attached to the benzene ring, right? The phenyl group is attached directly to the carboxylic functional group. Under this case, two effects are operating here. The first effect is, I will write here one, that is minus I effect, which is called as negative inductive effect, and the second effect is minus M effect, that is negative mesomeric effect. Now minus I effect is because of the phenyl group of the benzoic acid. So if I write here phenyl group, I hope you are able to see this, right? Then followed by C double bond O, then followed by OH, or I can write O minus. Since it is an acid, it has already given what? H plus. Now as I said that it is showing a minus I effect, it means that the electrons are moving towards the phenyl group. When it is moving towards the phenyl group, then I can just write this part, okay? If I just again fill this by OH, okay, then that is what O and H, okay? These bonding electrons are taken by these electrons, right? And meanwhile this H is going in the form of what? H plus. The negative charge is present on oxygen atom, and these electrons are moving towards what? The benzene ring, and thus we can say that the effect is minus I effect of this phenyl group. So therefore we can say that minus I effect of a phenyl group is giving H plus. It means it is increasing the acidic strength, right? And the second one is minus M effect. Minus M effect of the carboxylic functional group. This we have to understand. So I'll be writing here, right? So therefore if I write this benzene ring here, and then if I write C double bond O, then followed by what? O minus. Since it has already given one H plus, that is an acid, I'll be writing here, right? Now the pi bonds of the benzene ring. Now as I have told you that minus M effect of the carboxylic functional group, right? So what happens here is that if this pi bond gets localized here, then this bond will be what? Moving here, right? So therefore I can write the resonating structure in this manner. Now benzene ring, double bond C, then followed by O minus, then here also what? O minus. Then here we are getting a positive charge, and then followed by what? These two pi bonds. By this phenomena, that is what? When the pi electrons are moving towards this what? Group, right? moving towards this group means the group itself is taking the electrons. Which group? The carboxylic functional group. When it is taking electrons, one can see that it is increasing the negative charge on the oxygen atom. When the charge is increasing, that is negative charge, when it is increasing on the oxygen atom, it is destabilizing this benzoate anion. Thus it is going to decrease what? The acidic strength, right? Now let us have in a detail explanation. The minus I effect of the phenyl group, which is going to increase the acidic strength by dispersing the negative charge on the benzoate ion. So here, okay, I'll write here number 1 at the bottom. You can see that this is number 1 structure here, right? So here I will show the electrons movement towards water, this benzene ring, that is what phenyl group. If it is taking the electron, then this negative charge is dispersed on this water benzene ring, right? So therefore what happens, if a hydrogen was present here, now this is called as benzoic acid, then obviously these bonding electrons would have been taken by this oxygen and they were moving towards the ring, and thus one can say that the H plus is going in the form of, the hydrogen is going in the form of water, H plus. So therefore minus I effect of phenyl group is going to increase the acidic strength by dispersing the negative charge on the benzoate ion, right? Meanwhile the second effect, that is the minus M effect. Minus M effect of which group it is? That is carboxyl functional group. Okay, this group tends to destabilize the benzoate anion. How? By increasing the negative charge on the oxygen atom, due to which acidic strength goes on decreases. Now let me write the resonating structure here as 2, right? So here what happens, this pi bond is moving towards this carbon and this carbon here in the form of what? A double bond, right? When this bond is moving here, this carbon becomes a pentavalent and this bond gets shifted here. So then I can write another resonating structure here, that is resonating structure number 3. So here already single bond was there, now there is a formation of double bond, right? And when this bond has, that is what I am showing you in the form of red ink here, okay? When this bond is going to shift here, now this ortho carbon is bearing which type of charge? Positive charge, and the remaining electrons will be water as it is, right? And we now get another resonating structure, that is resonating structure 4. Now whatever the positive charge that is present in structure 3, in order to stabilize this positive charge, right, these bonding electrons will shift between this bond here, right? So therefore now I can write that structure in as 4th. Here double bond will be possible and that positive charge will be now present on this para carbon atom, and the remaining double bond will be present as it is. Now in a similar manner, this positive charge is compensated by shifting of these electrons here, due to which in resonating structure number 5, the positive charge will be now present on this carbon atom and the remaining double bonds will be present as it is. In all these resonating structures, that is 2, 3, 4 and 5, one can see that the oxygen atoms are having what? A negative charge. It means the charge of this oxygen bearing negative charge is not dispersed. It means there is increase in the negative charge on the oxygen atom, due to which the benzoate anion is destabilized. As a result, the acidic strength will be what? Decreasing. It can now be visualized that minus M effect has a greater magnitude than minus I effect. As a result, the overall acidic strength tends to what? Decrease. Therefore, benzoic acid is a weaker acid than formic acid. That I have just mentioned in the below part here. I hope you are able to see this, right? It is noted that minus M effect has greater magnitude than minus I effect. As a result, overall acidic strength tends to what? Decrease, and thus one can say that benzoic acid is weaker than formic acid. Now we shall study the effects of substituents. The substituent can be either electron donating or electron withdrawing, right? So effect of substituents on acidic strength of aromatic carboxylic acids, and this effect of the substituents on the acidic strength of aromatic acids, it is going to depend on the following factors. There are two factors. The first one is nature of the substituent, whether it is an electron donating substituent such as alkyl group, or whether it is an electron withdrawing substituent such as nitro group. Fine. And the second factor is the position of the substituent in the ring, whether it is present at ortho position or at meta position or at para position. Now, before going to further studies the effects of the substituent on the acidic strength of aromatic carboxylic acid, one has to understand the ortho, meta and para. So here we are having benzene ring, so I will write here 1. So in case of this benzene ring, all the ring carbon atoms are identical. Identical in the sense all are sp2 hybridized. When there is no substituent on benzene ring, and if benzene ring is just C6H6 or the geometrical representation whatever I have done here, there are no positions. It means there is no ortho, there is no meta and there is no para positions in benzene ring, right? And when benzene ring undergoes a reaction, basically it is an electron rich species, right? So therefore it is acting as a nucleophile, and henceforth benzene will always be undergoing predominantly electrophilic substitution reaction. Fine. And when it undergoes an electrophilic substitution reaction, okay, I'll take one example so that you will be understanding, right? So if this is benzene ring, and if at all if I subject this benzene to chlorination in the presence of anhydrous AlCl3, then benzene will be converting into what? Chlorobenzene, along with the formation of what? HCl. Here there were no ortho, meta and para position, right? All were what? Identical. But when it is subjected to chlorination, that one of the Cl, right, it can go and be present on any of the carbon atom of benzene, either here, here or here or here or this carbon, right? Wherever it is present, then it is undergoing a substitution, and that substitution is mono substitution. So here we are getting here one Cl here. Now this is called as what? Chlorobenzene. Fine. Now in this chlorobenzene, all the ring carbon atoms are not same, right? So what I can write here is that this is the Cl group now, okay, which is present on this carbon. Now the adjacent carbon atoms with respect to what? This Cl, okay, the adjacent carbon atom with respect to this Cl, these are called as what? Ortho carbon, or it is simply called as ortho position. Fine. And the next two immediate, okay, this position and this position is called as what? Meta position. and the one which is directly opposite to that of what this Cl is called, this position is called as what? Para carbon or para position. Now do not fix in your head that Cl should be always be present on this carbon only. Okay, I will be writing here once again. Do not fix that in your head that Cl or any other group should be present on this carbon only, right? It can be present on any of the carbon atom. So I'll be writing here once again now. So if I write it the Cl as here, now this carbon is called as ortho and this is called as ortho. This carbon is called as meta and this carbon is called as meta, and the one which is opposite to the Cl is called as what? Para. Is it clear, students? Now I have written here another structure. This I call it as number 2. Okay, and here you can see that on benzene we are having here A, right? This A can be a halogen, it can be a nitro group, or it can be a carboxylic functional group, or it can be what? The ether linkage, that is OCH3. If X is equal to Cl, it is called as chlorobenzene. If A is equal to X, it is called as chlorobenzene. If A is equal to Na2, it is called as nitrobenzene. If A is equal to carboxylic functional group, then it is called as benzoic acid, right? So I'll be writing here benzoic acids, right? So C double bond O, then followed by OH, right? And if A is equal to OCH3, then that becomes what? Anisole, or simply called as methoxybenzene, right? So this becomes benzene ring, then followed by O, then followed by CH3, which is simply called as methoxybenzene. Now I'll be taking this benzoic acid and remaining thing I'll be erasing and explaining with one of the substituent called as nitro group substituent. Now we are having benzoic acid. So basically we know that this bond, whatever is here, it is taken by this O, that is what? Oxygen, and H is expelled in the form of what? H plus, right? But now if we are having a substituent here, that is what? NO2 group, right? N double bond O and single bond O, right? It is called as ortho-nitrobenzoic acid. And the nature of this group is to withdraw the electron. So therefore NO2 group is what? Electron withdrawing group. So therefore first let me write what the resonating structures of what? Nitrobenzene, right? So this is benzene, then followed by N double bond O, single bond O minus, then followed by what? Positive charge. Since valency of nitrogen is 3, it has exceeded. Here we are having what? 4, right? So therefore it bears positive charge. And nitro group is an electron withdrawing group. Then what happens? This pi bond will be moving here. Nitrogen, which was tetravalent, now becomes pentavalent. So therefore this bond will be moving towards oxygen. And I can write the one more resonating structure in this manner here. Fine. Then I can write a double bond nitrogen, single bond O, a positive charge on this nitrogen, single bond O minus, and here this orthocarbon, right? Because already we have learnt whenever one substituent is present, then this carbon is called as what? Orthocarbon. So therefore orthocarbon is now bearing what? Positive charge, and remaining pi bonds are present as it is. And this positive charge, in order to compensate, these bond will be migrating here. So now I can write one more resonating structure. I hope you are able to see this. Double bond nitrogen atom, a positive charge, single bond O minus, again single bond O minus. Here the double bond will be present and the positive charge will be moving now towards paracarbon, and remains what? Here double bond. Now since this positive charge cannot be what? Present on that carbon, paracarbon, these bonding electrons will be migrating here, and therefore I can write one more resonating structure, that is double bond nitrogen, a positive charge, single bond O minus, single bond O minus, a double bond here and a double bond, and here what? One positive charge. So I call this as A and this as B and this as C and this as D. Fine. In B, C and D, you can see the positive charge is present at orthocarbon and at paracarbon and again at orthocarbon atom. Now B and D are both the same. Why? Because both are having positive charge on orthocarbon atom. So therefore I will write B and D are nothing but in this manner. Fine. So that is benzene ring I'll write here now, and rather than writing that complete NO2 structure, I'll be just writing now NO2, right? So this is nitrobenzene. But now if the orthocarbon was having a C double bond O and then followed by OH, now I can say that this nitro group is an electron withdrawing group. It withdraws the electron from orthocarbon atom, right? Because orthocarbon is now bearing which type of charge? Positive charge, right? So therefore what happens that now this carbon atom bearing the positive charge, it seeks electron. From where it seeks? From this carbon atom, and this carbon atom seeks from this oxygen atom. So therefore what this oxygen does, it will take these bonding electron towards itself and the electrons will be moving towards what? This orthocarbon. Meanwhile what happens? H plus will be going with a greater speed to give what? H plus. So therefore now we can say that if we are having a nitrobenzoic acid, then it is what? An acidic more when compared with what? Benzoic acid. And the similar thing will be happening with respect to what? That is structure C. If we take structure C and if I write it as what? In this manner, benzoic acid, right? And here if I write what? NO2, and here if I write C double bond O and single bond OH, this NO2 group is an electron withdrawing group. It is going to withdraw the electron, and because of that orthocarbon and paracarbon will be now having what? Positive charge, and because of this positive charge, in order to compensate this positive charge, this carbon is going to withdraw the electron from this oxygen, and this oxygen will withdraw the electron from this bond, and H plus will be going at a greater speed to give what? H plus. Concept is clear, students? But one thing we should remember, that if the NO2 group is present with respect to carboxylic functional group at meta position, okay? So if I write here NO2 here and if I write here COOH, fine? So NO2 group is an electron withdrawing group. We know that now, fine? So it is going to take the electron from orthocarbon and from what? Paracarbon. But this NO2 group is not having any effect on this what? Metacarbon atom. It is not bringing any positive charge on metacarbon by seeing the resonating structure A, B, C and D. Okay, there is no such positive charge on this metacarbon atom. So therefore meta-nitrobenzoic acid is less acidic in nature. So we were discussing what are the second position, the second point, that is position of the substituent in the ring, whether at ortho or at meta or at what? Para. Fine. So we are having the acid constant, that is acidity constant values, K values for nitro substituted aromatic acids at 298 Kelvin, right? Since NO2 group is an electron withdrawing group, it is going to increase the acidic strength. So here I have written the 3 nitrobenzoic acid. The first one is orthonitrobenzoic acid, the second one is para-nitrobenzoic acid, and the third one is meta-nitrobenzoic acid. As already discussed, we already know that, okay, if the NO2 group is present at ortho position with respect to this functional group, then this carbon atom bears positive charge. So therefore the K value for this is 670 into 10 to the power of minus 5. If the Ka value is 36.0 into 10 to the power of minus 5, then it is nothing but the nitro group is present with respect to carboxylic functional group at para position. Fine. And as I've already told you that in the third one, okay, the NO2 group is present at meta position. If it is at meta position, then obviously it is having no effect with respect to this C double bond O, right? So if I say this as a functional group, carboxylic group as a functional group, then this carbon is called as which type of carbon? Meta carbon atom. Fine. And for this we are having the Ka value 32.0 into 10 to the power of minus 5. So we now know that larger the Ka value, stronger is the acid. So therefore we can say that first one, that is what ortho nitro benzoic acid is a stronger acid when compared with what para nitro benzoic acid. So therefore I can write in this manner. So first one is orthonitro benzoic acid, second one is para nitro benzoic acid, and the third one is meta nitro benzoic acid. Is it clear, students? So far we have discussed with respect to the substituent group, which is electron withdrawing group. Fine. Now we are going to discuss with electron donating group. Now similarly, the Ka values for methyl substituted, which are simply called as toluic acids, okay, at 298 Kelvin are as given. So the first one is called as orthomethyl benzoic acid, second one is called as metamethyl benzoic acid, and the third one is called as paramethyl benzoic acid. Before going to this, first let us write the structure of resonating structures of what? Methyl benzene. Fine. So if we write the resonating structures of methyl benzene, we can conclude that in this manner, right? So I am having here benzene ring. Fine. And then let me take here methyl group. Methyl group is an electron donating group. When it gives electron, it goes to the orthocarbon atom. So therefore I can write now in the form of, I'll write here double bond, then followed by what? CH2. In fact, I should write here CH2 then followed by H. If this bond is forming a bond here, then what happens? This bond will be going to the orthocarbon. So therefore orthocarbon is now bearing negative charge and remaining will be as it is. Fine. And then I can write one more resonating structure that will be in the form of double bond then followed by CH2, and this negative charge cannot be present on this carbon. So this negative charge will be moving into the ring between this carbon and this carbon, right? So therefore this pi bond will be moving to the next carbon. So now I can write a double bond between these two carbon and a negative charge on para carbon atom, and the remaining pi bond is as it is. Now this negative charge will form a bond between these two carbon atom, and the pi bond will be moving to the next carbon atom. Fine. So therefore now I can write one more resonating structure, that is double bond then followed by CH2, a pi bond, here also pi bond, and here one negative charge. And this negative charge will be forming a bond here, and these electrons will be going to that carbon atom. So I can write the remaining resonating structure in the form of methyl benzene, pi bond here, and then followed by water CH3. So I will call this as 1, 2, 3 and 4. Fine. Let me take this second one. Okay, second one, that is at para carbon we are having what? A negative charge. Fine. So if I write that structure here and then followed by double bond, and here one negative charge, and here a double bond then followed by CH2. Now let us imagine that at this para position there is a functional group called as what? C double bond then followed by OH. Fine. So we now understood that this methyl group is an electron donating group. It will be giving electrons to benzene ring, and when it gives the para carbon is having what? A negative charge here, right? The para carbon is having negative charge. Now this negative charge will be dispersing through this what carbon, then followed by this oxygen. So therefore oxygen becomes what electron rich species, okay, and it loses its electron withdrawing tendency from this OH bond. This is not happening. If this is not happening, then this bond remains intact, which means hydrogen remains here only. So therefore electron donating group decreases the water acidic strength of carboxylic acids. Is it clear, students? But here there is one exception, okay. That exception is when a methyl group is present in case of number 1, okay, when methyl group is present at ortho position, okay, at ortho position, it is an exception, okay. It will be having larger Ka value. Ka value, you can see that 12.4 into 10 to the power of minus 5, okay. We know that concept, larger the Ka value, stronger is the acid. So therefore I can now say that this ortho methyl benzoic acid is a stronger acid when compared with what meta methyl benzoic acid, and in turn meta methyl benzoic acid is a much more stronger acid when compared with what paramethyl benzoic acid. Is it clear, students? And we should remember that when the methyl group is present at meta with respect to that carboxylic functional group, it is always what less acidic, because it is not going to bear any negative charge. So you can see in the resonating structure 1 or 2 or 3 or 4 the metacarbon I will be indicating. So this is metacarbon, this is metacarbon, here also meta, here also meta, here also meta, here also meta, right? So in meta position there is no negative charge. It means that whenever the carboxylic functional group is present at meta position with respect to an electron donating group, then it is having no effect. It will be always what a much stronger acid when compared with that of the ortho and that of the methyl benzoic acid. Now to conclude the explanation, okay, from the Ka values, okay, it is evident that with the exception of orthoisomer, okay, orthoisomer is an exception, right, both para and metatolvic acids are weaker acids, because here we are having electron donating group, okay, than benzoic acid. I repeat it once again, both para and metatolvic acids are weaker acid when compared with that of benzoic acid, whereas the three, that is what isomeric nitrobenzoic acid, that is paranitro, metanitro and orthonitro, are stronger acids than benzoic acid. Why? This is so because NO2 group is an electron withdrawing group, right? So wherever NO2 group is here, all the three nitro isomeric benzoic acids are much more stronger acids when compared with the benzoic acid, that is a C6H5COOH. Fine, students. Now let us try to understand the effect of different substituent on benzoic acid. Now in this chart you can see that I have written the heading acidity constants of substituted benzoic acid, right? And the Ka value of benzoic acid, one has to remember, it is what 6.3 into 10 to the power of minus 5. Is it clear, students? Now in the first column you can see that here I will be writing 1 and this is 2, okay, this is 3 and this is 4 and this is 5 and this is 6, right? So in the first column I have written acid and here I have written P. It means that it is nothing but a nitro group is present at para position, okay, so the compound is paranitrobenzoic acid. And in this row I have written here M, it means it is metanitrobenzoic acid. Here I have written O, it means it is orthonitrobenzoic acid. In a similar manner for the second one, so here 1, here 2, here 3, I will change it, okay, rather than writing 1, 2, 3, let me write it as what? A, okay, then this is B, this is C, this is D and E, okay. Fine. So A, that is with respect to substituent called as nitro, where that nitro group can be present at para position or at what meta position or at what ortho position. Similarly in B, if it is having Cl, then it can be present at para position or what meta position or what ortho position, right? So A in that A, first we are having para-nitrobenzoic acid. So para-nitrobenzoic acid, the Ka value is 36 into 10 to the power of minus 5. And if the NO2 group is present with respect to meta position of benzoic acid, then it is 32 into 10 to the power of minus 5. And if the NO2 group is present with respect to the COOH group, that is at ortho position, then it is nothing but 670 into 10 to the power of minus 5. I'll be just highlighting the names of the compounds so that it becomes very easy for you to remember. So B, para-chlorobenzoic acid, meta-chlorobenzoic acid, ortho-chlorobenzoic acid. In case of C, para-methyl benzoic acid, meta-methyl benzoic acid, and here ortho-methyl benzoic acid. In the case of D, para-methoxy benzoic acid, meta-methoxy benzoic acid, ortho-methoxy benzoic acid. In the case of E, para-hydroxy benzoic acid, meta-hydroxy benzoic acid, and ortho-hydroxy benzoic acid. Fine. You can see the Ka values there. And one has to remember, larger the Ka value, stronger is the acid. And now I want to say you that if you see the column number 6, okay, here, okay, if you see this column number 6, the Ka values, okay, the Ka values for all those groups, okay. So if it is at ortho-nitrobenzoic acid or ortho-chlorobenzoic acid or ortho-methyl benzoic acid or ortho-methoxy benzoic acid or ortho-hydroxy benzoic acid, fine. So these are present at ortho. So when these are present at ortho, you can see that the Ka value is almost larger for all these groups, right? So one can now notice that which groups are electron donating and which groups are electron withdrawing. Fine. NO2 group, I have already told you that it is an electron withdrawing group. Fine students, NO2 group is which type of group? Electron withdrawing group. Fine. And now you see the methyl group. Okay, methyl group is an electron donating group. Fine. So whether the group is electron donating or whether the group is electron withdrawing, but if these such type of groups are present at ortho position with respect to that carboxylic functional group, these are always stronger acids having a larger Ka value. Okay. And this phenomena is called as what? Ortho effect, which is beyond the scope of your NCERT textbook. When it comes in competitive, we will be discussing that part also. Is it clear, students? Now, there is explanation for electron donating groups. Okay, so here EDG I have written. Fine. So in the case of electron donating group such as methyl group, there is an increase in the electron density on the benzoate ion. Fine. So as a result, the ion becomes unstable and acidic strength goes on decreases. Fine. The acid weakening effect is more pronounced, okay, when the substituent is present at what? Para position than at what? Meta position. One has to concentrate only on para and meta. Why? Because I have already told you whether the group is electron donating or whether the group is electron withdrawing. If it is present at ortho, it is almost and always a stronger acid. So therefore for us it is very much important to consider only the meta position and that of what? Para position. So when we are having the benzoic acid, right, and if at all if I write here COOH, right, and if I write the methyl group here, then it will be acting as a donating group. It will donate to this carbon, ortho carbon here, and at what? Para carbon. Fine. So if it is ortho carbon, if the COH group was here, okay, then obviously it would have been what? A stronger acid, but we know that it is almost stronger only, so we have to concentrate only on what? Meta and what? Para. So therefore if I write here with respect to meta, then if I write here COOH and then followed by CH3, now this is methyl group which is present at what? Meta with respect to this functional group. Fine. If at all if this is acting as an electron donating group, it will donate to what? This carbon and this carbon and this carbon. Why? Because these two are ortho with respect to this methyl group and this will be para, isn't it? So therefore one can say that the acid weakening effect is more pronounced when the electron donating, that is methyl group, is present at what? para position than at what meta position in the ring. Fine. And now we'll move towards what the electron withdrawing group. Fine. What happens if we are having what electron withdrawing groups? Now, in the case of electron withdrawing group such as NO2 group, there is a decrease in the electron density on the benzoate anion. Why? Because we know that electron withdrawing group means it withdraws the electron. As a result, the benzoate ion becomes more stable and acidic strength goes on increases. Okay, there if it was electron donating, we were saying that acid weakening effect, right? So here the group is electron withdrawing, so therefore we have to say that it is the acid strengthening effect is more pronounced, right, when the substituent is present at para position than at meta position in the ring. Here also one has to remember that if the electron withdrawing group is present at ortho position, it is always a stronger acid only, and that we have already written one note here lastly, right? Both electron donating group and electron withdrawing group tend to increase the acidic strength of benzoic acid when these are present at ortho position, and this is because of the phenomena called as ortho effect. Is it clear, students? I hope that you have understood, and kindly go through this. If you are having any doubts, we'll be clearing those doubts also. Thank you for watching this video. If you feel good, kindly like the video, share the video and subscribe to my channel. Thank you so much.